All right, let's talk about a material that honestly sounds like it came straight out of science fiction: titanium. It's the metal that builds our jet engines and our spacecraft, and it's even the stuff we use to rebuild the human body. But this supermetal has a really big secret, a central puzzle that we're going to solve today.
And here is that puzzle. Titanium is everywhere. I mean, it is all over the Earth's crust. It's actually more common than copper or nickel or lead. So if there's so much of it, why did humanity build entire civilizations with all these other metals while titanium just sat there, completely untouched for thousands of years?
Well, the answer is kind of a paradox. To get it, we have to first look at what titanium is actually like, its basic nature, which makes it both incredibly common and, at the same time, incredibly hard to get your hands on.
See, the reason all comes down to its chemistry. Titanium is super reactive. It has such a powerful attraction to oxygen that you almost never ever find it just by itself in nature. It's always bonded to something else, locked away tight inside mineral ores, just waiting for someone to figure out how to set it free.
And freeing it, yeah, that is not easy. Traditional smelting, the way we've been making iron for millennia, it just doesn't work, not even close. It actually took until the 1940s for us to figure out a way to do it on an industrial scale, a method that could finally wrestle titanium into its pure form, the incredibly complex Kroll process.
So how does this crazy process work? Well, first you take the ore and you hit it with chlorine gas and carbon at blistering hot temperatures. This makes a liquid called titanium tetrachloride. Then, after you purify that, you react it with molten magnesium inside a chamber with absolutely no oxygen. Because remember, titanium will grab onto any oxygen it finds. And the result of all this isn't some shiny metal bar. Nah, it's this weird, porous, brittle stuff they call titanium sponge.
And we're still not done. This sponge then has to be crushed up, cleaned, and then melted down, and not just once, but usually multiple times inside a special vacuum furnace, to finally get a pure, high-quality ingot of titanium. It is, without a doubt, one of the most energy-intensive metal-making processes on the entire planet.
So, after all that incredible effort, you have to ask, was it worth it? Oh, absolutely. Because the metal that comes out of this fiery process has a combination of properties that pretty much no other element can match.
The big headline feature, the one everybody knows, is its incredible strength-to-weight ratio. I mean, titanium is as strong as many types of steel, but it weighs about half as much. For anything that needs to be both strong and light, think an airplane or a spacecraft, this is basically the holy grail of materials.
But it's got other superpowers too. It's almost completely immune to corrosion. Why? Because it forms this thin, protective layer of oxide on its surface that instantly repairs itself if it gets scratched. It's also biocompatible, which means the human body doesn't reject it. In fact, our bones can literally grow and fuse directly onto it. Oh, and it holds its strength in temperatures that would make other metals just give up.
So, with a resume like that, where does it all come into play? Well, it turns out titanium isn't just some scientific curiosity, it's a critical part of some of our most advanced and important technologies.
In aerospace, it means lighter, more fuel-efficient planes and spacecraft that can handle the extreme forces of launch and orbit. In medicine, it gives us durable hip replacements and dental implants that can last for decades. In the industrial world, it's used in desalination plants that turn salt water into drinking water. And yeah, you can even find it in high-end stuff like lightweight bicycle frames and tough-as-nails watches.
So you might be thinking it's all about jet engines and hip replacements, right? That's where it all goes. But what if I told you that the single biggest use of titanium is something you probably see dozens of times every single day, and you don't even think about it?
Just take a look at this. It's kind of shocking. A staggering 95% of all the titanium we process from ore is not used to make metal. All those incredible things we just talked about, they only account for about 5% of all the titanium we use.
So what's in that massive 95% slice? It's used to make something called titanium dioxide, which is the single most widely used white pigment in the world. It is what makes your paint opaque, your plastics bright white, and your paper brilliant. It's even the key ingredient in sunscreen that blocks harmful UV rays. It is literally everywhere.
So we've got this amazing material, used for everything from spacecraft to wall paint. But, given how incredibly hard it is to produce, what's the cost? Let's talk a little bit about its environmental footprint and where it's headed.
Look, there's no getting around it. Making new titanium from ore is an energy-hungry, high-emission process. That's the big downside. But on the other side of the coin, the metal's extreme durability means things made from it last a very, very long time, so you don't need to replace them as often. And maybe most importantly, titanium is highly recyclable.
And this is where the story gets a lot smarter. Recycling titanium metal uses way less energy than making it from scratch. The aerospace industry, for example, generates a lot of clean scrap metal when they're building parts, and a huge amount of that gets collected and melted right back down to be used again. It creates a much more sustainable loop.
So, from a hidden gem locked in the earth to a critical piece of our modern world, titanium's journey is just one of incredible scientific and engineering achievement. As we keep pushing for technology that's more efficient, more resilient, and more advanced, you can bet this space-age metal is going to continue to play a huge role. The only real question is, what new challenges are we going to solve with it next?